Okay, so we have seen in the previous videos things about random variables, and those random variables were single dimensional. Now coming to two-dimensional random variables, the same thing. Actually, if it is 1D, then all of us know that of course, the random variable will take all the values from the real line. And we all know that probability always ranges between probability of any variable ranges between 0 and 1. It's a 0 for an unsure event and 1 for a sure event. Now coming to a two-dimensional random variable, I mean two-dimensional as it says 2D, so it would be on R cross R. Okay. First, let's define certain things in two-dimensional random variables, like how we have defined for single dimension, and then we will go to the remaining things of solving problems and all. Let capital X and capital Y be the two random variables, defined on same sample space, If they are defined on different sample spaces, then again we cannot go with comparing things between them. Okay, on same sample space S. Okay, then sample space yes, then the function f of capital X comma Y, f of capital X comma capital Y, that assigns a point in R2. As I have said, R cross R, R2, a function that assigns a point in R2 is called a two-dimensional random variable. Okay. That means what? It will be like this. It will have ordinate and abscissa. It will be something like this. Okay. Yeah. Now, obviously, like how we have defined probability mass function and probability density function in the previous videos, that is for discrete random variable. We'll be having discrete random variable with its probabilities would be called probability distribution function, and when it is discrete, it would be called probability mass function. Similarly, continuous random variable with its probabilities, it would be called probability distribution function, named as probability density function. Density function for continuous, mass function for discrete. Now, similarly for 2D also, we ought to define the probability mass function and then the probability density. Once I define the probability mass function, then things will follow for probability density function. Continuous, I'll be integrating. Discrete is just the summation, as you all know. Discrete is summation, continuous is integration. Okay. Now, let's see how we will write the probability mass function. 2D probability mass function. It would be called actually joint probability distribution or joint probability mass function. 2D, two-dimensional, or joint. Either of the names. Joint means together. Joint probability mass function. Mass function. If you understand it, things will be very easy. The table associated with the two variables, if you understand, it looks a bit complicated, but then things behind it are very simple. I'll just do it for 2 or 3 values, because if I write too many values, then it will look very huge and it will be probably confusing to you. X is towards this side and Y is towards this side. So I'll be having Y1, Y2, Y3 and Y4. Let's suppose I am taking only till Y4. Similarly here, X1, X2, X3, X4. Both need not be same, but then here I am doing it like that. Now you see here, probabilities associated will be something like this. P11, P21, P31 and P41. Okay. X is 4, Y is 1. X is 3, Y is 1, like that. P12, P13, like your matrices only, guys. You will be calculating also accordingly. Formula is very simple, but first you understand how to write, then things would be very easy. Okay. P23, P24, P32, P33, P34. Similarly, P42, P43, P44. This is how I'll write the 2D, two-dimensional probability mass function or joint probability mass function. Okay. Now, if I take the sum, they'll be called marginal densities. I'm sorry, they'll be called marginal probability functions. Okay, I'll just define them. But then before going to it, just see how these are calculated. Suppose if I have the probability like this, letter A is equal to like this. A less than capital X. Sorry. A less than capital X less than B. And B is what? C less than Y less than capital D. These are two events. Okay. Then if I have to calculate probability of A less than or equal to X less than A less than X less than B, C less than X less than D. If I have to calculate this, it's just nothing but the intersection of A and B. That's it. That's how it's defined. Okay. Of course, if equal to is there anywhere, A also will be included. If equal to is there here, B also would be included. Okay. Yeah, actually for this, it is defined like this. For A less than, X less than or equal to B and C less than Y, this is Y less than or equal to D, it is defined like this. Okay. Yeah, C less than, Y less than or equal to D, it is defined like this. What's this? This is how I'll be finding the joint probabilities. Joint probabilities I'll be finding. Okay. Another version of writing it, I'll just show and then close this video. The function P on the sample space where X is defined cross the sample space Y is defined is defined as, this is the important one actually. The previous one is just a opening kind. Okay. So this is defined as, notated as Pij. This is equal to P of X is equal to Xi intersection Y is equal to Yi. This also can be written as P of Xi comma Yi. Okay, this is how actually it is defined. It's a similar version of it as well here. Okay, this would be Pij would be called the probability function of X and Y. Probability function of X and Y. Okay. And the things that we have represented in this table, P12, P13, all this have originated from this formula. Okay. In the next video, we will see marginal probability function. I'll just stop here.